In this video, we work another implicit differentiation problem. This problem involves the logarithm as well, but this time it's not easy to solve for x as a function of y or y for as a function of x. So we've got this natural log of y squared and 2y term in our relation. If we were able to get rid of that natural log by exponentiating, we'd end up with an e to the 2y somewhere in our equation, and we could never get rid of that logarithm and the exponential at the same time. So we can't solve for y. And if we just had one term involving x, we might be able to solve for x in terms of y, but we've got this 4x cubed in the 2x term. I understand that there is a cubic equation so that you can solve for the roots of a cubic in terms of the coefficients if the equation is ax cubed plus bx squared plus cx plus d. But I actually don't know how to do that. I can't even solve that cubic equation in terms of coefficients a, b, and d. We could say a is 4, b is -2, and then c is 0, and then d is this function of y, and we might be able to solve for y that way if we had that cubic equation, but we don't, or solve for x as a function of y that way. But I don't actually know how to do that. So we actually have to use implicit differentiation in this case, given my constraints, given the fact that I can't solve for x in terms of y or y in terms of x to compute the derivative. So this is what we would do. Usually I do this on paper, but we can do it just by typing it. We're going to differentiate both sides of this equation with respect to x. So on the left-hand side, we're going to have the derivative with respect to x of this equals the derivative with respect to x of the right-hand side. And I don't actually want to graph anything. I just want to type that equation, and then we'll compute the derivative term by term. The derivative of 4x cubed with respect to x is 4 times the derivative of x cubed, which is 3. So you bring the exponent down, then you multiply by x to the 1 less power. And then the derivative of natural log of y squared is the derivative of natural log of a function of x. And that function of x is that y of x squared. So the derivative will be 1 divided by that function of x, which in this case is y squared, times the derivative of the inside with respect to x. So that requires the chain rule as well. So we're going to have 2 times the inside function, which is y, times the derivative of the inside, which is dy dx. So this 2y divided by the y squared, well, one of the y's will reduce. You'll end up with a 2 in the numerator and a y in the denominator. So that's a 2 over y times dy dx there. And then we add 2 times the derivative of y with respect to x. That's on the left-hand side. And that equals the derivative of 2x with respect to x. Derivative of a constant times x with respect to x is just a constant. So now you have this equation involving your dy dx. Your dy dx is here and here. So we've got 2 terms involving dy dx. And then there's this other term that doesn't involve dy dx. So we will subtract that term from both sides and then factor the dy dx out of these 2 terms on the left-hand side. So what we get is dy dx times quantity 2 divided by y plus 2 equals this 2 minus that 12x squared. And it keeps trying to add, it keeps asking me to add a slider for d, thinking that d is a variable, but of course I'm just using that for the differentiation operation. It's a little sunny out here, so I'm going to put my shades on. All right, so now we're trying to get dy dx by itself. You've got some options. You can get a common denominator first on the left and then multiply by the reciprocal on both sides. Or if you like, you can take this expression and divide by that and then clear the complex fractions. I think I would rather get a common denominator on the left-hand side first. So this is a 2 over 1. I want it to have a denominator of y, so I'm going to multiply by y and divide by y. And now that we have a common denominator, we can just add the numerators. So this is actually 2 plus 2y divided by y. And then in order to get dy dx by itself, we'll multiply by the reciprocal. So it keeps trying to let d have a value. We'll have dy dx equals that 2 minus 12x squared times y. So we're multiplying both sides by y and then divided by that quantity 2 plus 2y. All right, so now we've got dy dx as a function of x and y. And the only problem with that is we don't actually know what x is in terms of y or what y is in terms of x. We can solve this for x, but then we also would have an x cubed on this side. So then we really can't get the x by itself. Here we might be able to solve for y, but then we would have, well, y in terms of this natural log of y squared, so we can't get the y by itself. So we're kind of stuck. But that is our dy dx. We just found it using implicit differentiation. Now this is going to give us the slope at any point on the curve, and this is our curve. It's kind of a cool curve. But we have to be at a point on the curve for this to actually yield the slope. This is actually a function of two variables. It's undefined when y equals -1. This function of two variables would be defined at every point in the xy plane, except for y equals -1. But we're only interested in the value of this function at points on this curve. So we need to find points on the curve. To do that, and say, okay, well, what points in the curve am I interested in? Well, just pick an x value or pick a y value, and then we will find out where that, then we can draw a horizontal line or a vertical line. And wherever that horizontal line or vertical line intersects our curve, at that ordered pair, we know that that ordered pair is on the graph of the original relation. Then we can substitute that ordered pair into this function dy dx, which is a function of x and y, and that will give us a slope at that location. We'll have an xy pair and as well as a slope with a point and a slope. We can use point slope form of the equation of a line to find the equation of the tangent line there. So that's the plan. I just chose y equals 1 for simplicity. And I said, okay, well, where does y equals 1 intersect the original curve? And it looks like it intersects at x equals -1, y equals 1. But I'm not actually sure that that works because it's really hard to identify that point of intersection just by looking at the graph. So I need to substitute x equals -1, y equals 1 into the original relation. And that's this relation. And basically what I'm doing is I'm substituting x equals -1, y equals 1 into the left-hand side and the right-hand side, and then I'm seeing if they're equal. If they are equal, then we know that x equals -1, y equals 1 is on the graph of the original function. So when I evaluate the left-hand side at x equals -1, y equals 1, I get a left-hand side of -2. When I evaluate the right-hand side at x equals -1, and I would substitute y equals 1 on the right-hand side as well, but there's no y's on the right-hand side. So we just end up with 2 times that x value, which is -2. So the left-hand side and right-hand side are equal and at that ordered pair. So that point is on our graph. So we can graph it. We can label it. I think I want to get rid of that horizontal line now. That was just used to find that point of intersection. And then you say, okay, well, what's the slope? Where the slope was y times the quantity 2 minus 12 x squared divided by 2 plus 2y. If we substitute x equals 1, or excuse me, x equals -1, y equals 1, the x and y coordinates of that particular point on our graph to that equation of the tangent line, and I'll just put tangent sub 1 there. We get a slope of -2.5. And that seems reasonable. It seems like we might start here and then go down 2.5 and then over 1 to find another point on that tangent line. Seems like that might be the slope of the curve. And to be sure, we'll graph the tangent line. Hopefully it seems to have the slope of the curve. It should just lie very tangent, or should lie tangent to the curve, which means, I don't know, that it has the same slope. I know that that description was circular. So the equation of the tangent line is y equals the original y value there, and our y value is 1, plus the slope of the tangent line times the quantity x minus x naught or x sub 1. That x value is -1, so it's x minus -1, but subtracting -1 is the same as adding 1. So I just called that x plus 1. If I graph the tangent line, we see that is tangent to the curve. It seems to have the right slope, passes through the point, so we're good to go. Now we can do the same thing at other points on the curve. I wanted to choose one x value that corresponded to multiple y values, or a y value that corresponded to multiple x values. So I chose x equals 1 as well. I know that there's some symmetry there with this, but this graph actually isn't symmetric. We see that, there's no symmetry about the x-axis or the y-axis or anything. But I thought at x equals 1, seems like we've got 2 points of intersection there. So now that I look at it, x equals 1 looks like this. Doesn't it look like at x equals 1, the y value might be something like 0.5? I've got a y value here, which looks like about 0.32. If I zoom in, it's actually more like 0.294. And then I have a y value here. It looks like 0.5 at first, but that's a little too high. Maybe it's -1. So that 0.1, -1 is also on our curve, or it seems to be. When x is equal to 1, y could be this 0.27 or 0.28, 0.29, something like that. Or y might be -1. So we're just reading the graph, but we're never actually sure it's going to work until we substitute that xy pair into the original equation. So I'm going to evaluate this at x equals 1, y equals at 0.27. And so this is the left-hand side. Now I knew the right-hand side was going to be 2. And that's at 2 times my x value, which is 1, so I get 2. So I started adjusting that y value. Initially, I had a 0.27. And I saw that that was too low. And I said, well, what about 0.28? So that's too high. Well, maybe it should be 2.78. And that's a little bit too low. So maybe it should be 2.784. And that's a little too high. So maybe we should do 8.3 here. 8.31, no. 8.2, no, that's not it. I don't remember which point I just used. I think it was like 8.475 or something. No, it's much worse than it was before, isn't it? Oh, there we go. So now we have 2.00000096. Maybe. This is a little bit more than 2. So the left-hand side and the right-hand side are not equal. Oh, I used 278479. I think I made a mistake. I think it was a better approximation a moment ago. Anyway, I'm trying to get a better approximation. I had 8479 before. And that was the, that x value is, or that left-hand side value is very close to the 2. I actually made it worse. I don't remember what that value was before I started changing it. Trying to get closer to that 2, but I didn't get it. All right. So at this x value, or this xy pair, we say that's almost on the graph. I'm just going to treat it as if it is on the graph. So I'll graph that point and label it. And then if we evaluate the left-hand side and the right-hand side at x equals 1, y equals -1, we see the left-hand side and right-hand side are both equal to 2. So that point is definitely on the graph. So we can get rid of that vertical line now. To say, okay, well, what is the slope at each of those points? Well, the equation of the tangent line is right here. So if I evaluate that slope at y equals 0.278479, I substitute my y value, and this is 2 minus 12 times the x value. X is 1, so we substitute that. Then we have 2 plus 2 times the y value. We simplify, we get a slope of approximately negative 1.089. And then our tangent line has this equation, y equals the y value. So we've got that point that we estimated, plus the slope of the tangent times x minus the x value, that point of that coordinate, the x coordinate on our line. So we have that line there. We see that's tangent to the line, or to the original curve for the relation. So that looks good. And then we can evaluate that equation for the slope at x equals 1, y equals -1 as well. And we see that the slope is undefined. If that slope is undefined, that means the relation has a vertical tangent line. So that's the tangent line. And I don't know why it's having trouble like plotting that point at 1, -1. It's not giving me the little dot like I want it to. I really want it to show me that, like that dot there, but it just keeps disappearing. But that this tangent line is tangent to the curve. This tangent line is tangent to the curve at that location, and this tangent line is tangent to the curve at that location. So that's how we do that. We can find ordered pairs on the line by sketching a horizontal or vertical line and seeing where that line intersects the original curve. And then we can substitute those ordered pairs x, y into the equation for dy dx, and that will give us the slope of the tangent line. And if we want to, we can verify that that is the true slope of the tangent line by graphing that tangent line along with the curve, and you can see that it has the right slope if it seems to have the right slope as the actual curve itself. So that is how we do some implicit differentiation, and then how we can use a graphing calculator to find points on the points on the curve, and then the corresponding slope there and the tangent line there as well.